Nice. Okay. Welcome everyone. Super happy today to have this webinar and which is hosted by Pruna. So my name is Bertrand from Pruna, and I will be moderating this session. Just for information, if you have any questions, feel free to write them in the chat, and we'll try to address them, whenever it's possible. But today we are super happy to welcome Chenfeng Zhu from Together AI, a senior AI researcher, but also with a lot of great research on efficient models for both language models and image and video generation. I highly recommend to check the Google Scholar or Chenfeng because there are a lot of gems there. So do not hesitate to check this. And we are very excited to have you. And Chenfeng, whenever you're ready, the floor is yours. So go ahead. I will just mute myself, but I'm here. And if you have anything, just let me know.
Okay, thanks for the kind introduction. And hi everyone. It's very exciting for me to share my research, efficient machine learning for intelligent machines. So let's get started. Currently, machine learning model can create new possibilities in virtual world. For example, we could leverage larger model to teach virtual agents to speak and pen. On the other hand, we could utilize video diffusion model to generate very realistic and fancy videos just based on text description. So these machine learning models are so powerful. But can this machine model drive real intelligent machines? For example, science discovery machine, the robots, iPhone, autonomous driving cars, AR heads, or even your thing. It's very hard. This is because machine learning models are very inefficient. For example, the larger model, such as DeepSeek V3, it takes more than 100 seconds to generate a sentence of 200 tokens with one H100 GPU. On the other hand, the movie gen from Meta, it takes more than 10 minutes to generate a 16-second videos with 8 H100 GPUs. So these machine learning models are very inefficient. However, the intelligent machines, such as robots, or phone, or AR headsets, it needs real-time interaction in a streaming manner. That means these machines will receive the streaming input, and it will also output something streaming. So this interacts in a streaming manner, but this inefficiency makes it hard to deal with the streaming application. And my previous works, stream diffusion, enable real-time stream generation. So this is a demo from our previous works. So you can see our work can enable the users like me who never learn how to paint beautiful auto image in real time, just based on one iPad and plus desktop RTX 4090. But this was something previously very hard on 2023. On 2023, that the stable diffusion model can only run 1.25 FPS on RTX 4090, but we can make it run 91 FPS on RTX 4090. So how do we make it? Let me first recap what is diffusion model for you. Diffusion model is nothing but just different image distribution, or here we can see any data distribution. We are gradually adding noise until this clean data distribution transforms into a noise Gaussian distribution. And diffusion model is to utilize parameter to learn to denoise back, and basically generates the image based starting from the noise or Gaussian distribution. And now we are considering a streaming system. So imagine that I'm live stream and I want to translate my appearance into another step. So the input image streaming comes into the model. Let's say that we want to translate this image into another step. We will utilize a trained diffusion model to denoise step by step until it transforms into another image. And imagine, so let's remember that this is a streaming application. So when we finish denoise the first image, the second image is still waiting there, and we still need to denoise step by step again and transform it into another step. Apparently, this streaming application is very inefficient and underutilize the computational capacity. This is because it utilizes a sequential implementation. So what that means? It means that each image is sequentially dealt with by the diffusion models. And for different image, they're sequentially put together. And this is very inefficient. And let's remember, GPU system is very good at parallel computing. So how could you make you test the GPU capability to extract it? Actually, we just need to reorganize a little bit. So we transform the sequential implementation into a sequential batch implementation. And we propose a simple technique that is stream batch. So given one image, we can utilize diffusion model deal with the first step, but at the same time, the second image already comes in. But we don't have to wait. We can put them together and denoise them together. And the third image comes. We also don't have to wait, and we can put them together and denote them together. So this can achieve like much higher throughputs and make sure the output smoothly. So this is a very simple technique in our stream diffusion pipeline. We also compose this technique with other design machine learning algorithms and system this is a core design pipeline. It's also include our own design CFG classifier for better technique, and we also have compressed VAE, and we design some system level techniques like IOQ and caching strategy, and we also utilize some engineering trick like TensorRT and so on. So finally, we could make the image generation pretty fast, as shown in the left image. And on the right part, you can see that we can drag the elements, and we can transform the image in real time. And compared to popular use as diffuser pipeline, our streaming diffusion is customized for streaming application, and we can improve throughputs by a large margin for different models compared to the diffuser pipeline. And you can also easily utilize by just pipe install stream diffusion TensorRT. So this is our algorithm system core design method, and this work stream diffusion enables new possibilities for many different intelligent machines. Here is several demo I collected from internet, and I would like to share this with you. For example, the first image shows that users utilize it for AI mirrors. I'm not sure whether you can see the hear the voice.
We can hear it just.
Yeah. So the users utilize our tech to design this AI mirror with voice command. And another user is chief of innovation at DPT Studio. So they utilize our technique to translate the visible lights into auto image in real time. I think this is a very interesting application. And there are another user also try to utilize our work to visualize brain signal. For example, our stream diffusion can translate the brain signal into some different image to reflect the brain activity. So this is our stream diffusion, and our work also being integrated into some products. For example, this is one of one company's products. You can see that they utilize our work to do the AI live stream. However, we quickly find that the temporal consistency is not that satisfactory. So you can see that even though we can translate the live stream appearance into different style, it's very cool, but it keeps flashing and shaking during the translation. And the co-founder of this company quickly contact me, the Chenfeng. It's great work, but can you make this more temporal consistent? Yeah, sure. Let's try to make it more temporal consistent. So currently, video diffusion models have superior temporal consistency. For example, the one model, you can see, you can generate videos with very good temporal consistency. And there are also some different, really efficient video generation model. For example, the cause VID and self-forcing. So this track's work is very efficient, and it can also generate the very temporal consistent videos. Okay, so now we have temporal consistent video generation model. We also have the efficient video generation model, like cause VID and self-forcing. So can we utilize these generation models for streaming applications? So it looks like it's very natural that we can do it. Unfortunately, we can't. So currently, the video diffusion model still unmet the streaming serverless objective. Concretely, that we should make the video diffusion model meet two surface level objectives. The first one is the time to the first frame. So in real applications, so we should make sure the time to the first frame can be less than 1 or 2 seconds. For current video diffusion models, whatever one and this kind of bidirectional model or very efficient, let's say self-forcing or cause VID. So they deal with the video with a whole large chunk. So they cannot meet the required time to first frame. Another very important objective is FPS. So we should make sure that, or on the other hand, we should make sure that every input frame can generate output which can meet every deadline given a mixed time chunk. So that means we should improve the required FPS to ensure that every frame meets deadline. However, current video diffusion models can also hardly achieve the target FPS. So let's look at how current video diffusion model deals with videos. So in current video diffusion model, they treat the video input video as a bunch of chunk, and we can form it as a 1 times t times h times w. So usually the number of time frame is very large, and this can lead to the whole video diffusion model being positioned at a very heavy compute bound region. So it's really like bounded by the computational capacity of the hardware. And we try to resolve this problem by proposing SLO aware method. Here, we try to control the input size to adjust the hardware intensity. Specifically, instead of dealing with a whole large chunk of the fixed size input, we control the number of the frames to be small enough, and we can dynamically adjust the batch size. So this enables us to make the whole pipeline have the flexible computational intensity on the roofline model as shown here. So you can see that we can adjust the input size to make the whole the algorithm intensity can transfer from memory bound to compute bound to memory. So we make them like that. We can make them dynamic adjust. And more specifically, so we give an example here. We want to keep the frame number small enough. For example, we want to keep the t equal to 4. So this is very small number of frames. And we can try to reduce. So basically, if you can reduce the number of t, so we can reduce the time to the first frame less than 0.5 seconds. You can see compared to the previous method like 1.2.1 on the course VID, our method can achieve the live stream objectives. And you can see that we can also, and you can see that with our careful design to adjust the size of the inputs, we could control the SLO tail latency metric, let's say P99. As you can see that our P99 time to the first frame is only 585 milliseconds, so which fully satisfies the live streaming requirement. And you can see that our miss rate is also pretty low. For example, here we only have 0.2% of the miss rates. Compared to our baseline course VID is really high. So basically, we can control the input size to make sure we can achieve a very good test time to the first frame, the time to the first frame, and you can see that this is the visualization of our figure. Almost all of our streaming diffusion latency could be lower to the target. And another important metric is the FPS. So we make sure the time frame being smaller, we want to also increase the FPS. We can also control try to control another dimension of the input. So that is, we can control the batch size. So we accordingly increase the batch size B to improve the FPS. So as you can see, that just now I just introduced a technical stream batch in stream diffusion V1. We can also utilize the same trick in this video diffusion mode. So we can also utilize the same trick stream batch to improve the FPS. So as you can see that with the stream batch on one GPU, for example the H100 GPU, we can improve the FPS further. But we quickly find, even though we try to increase the batch size with one GPU in the one GPU, we can still hardly to achieve the target FPS. For example, in the live stream application, we usually expect the FPS can be as high as 30, but now it's just one GPU. We still mostly can just reach 19. Here is the I think 26 for one step and 20 for the 500 resolutions. And we want to improve the FPS. How? So it's very intuitive for us that we can scale the number of GPUs. So if we cannot improve the FPS on one GPU further, so why not scale the number of GPUs? This makes sense because in live stream application, most of the serving platforms use the cloud instead of local devices. So we can provide them a scalable solution with more GPUs. However, we find currently pipelines has very poor GPU scalability. As you can see, by utilizing current popular parallelism technique like sequential parallelism, technique unices, and ring attention, increased number of GPU from 1 or 2 GPU cannot lead to linear FPS improvement. And if we increase the number of GPU to 4, the gain is still very trivial. You can hardly reach the target FPS. And we design a new method called I call it as the GPU scalable pipeline orchestration method. So as shown in this figure, we can split the workload equally to different GPUs. So when the first SLO aware chunk X1 comes to GPU 0, we can send the middle results to the GPU 1. At the same time, GPU the X2 comes in, and it is processed by the GPU 0. Then the X1 finishes the first linear steps, and X3 comes, and we can put this X1 and X3 together and denoise them together. So this is also the same idea of our previous stream batch, but this time we combine the GPU parallelism technique to make it more efficient. And I prepare animation for you to have a better visualization for our technique. So basically, it's just like orchestrate the GPU pipeline to improve the IPS. So you can see that this method can lead to almost linear IPS scaling. So for DIT blocks, we utilize 2 GPUs can lead to almost 2 IPS gain, 2 times IPS gain, and 4 GPUs can lead to almost more than 3 times IPS gain. So it's very good. We basically utilize SLO well chunk size, and with our GPU orchestration method, we can achieve target TTF the time to the first frame and the target FPS. But is that all? Unfortunately, no. So even though that we can make the efficiency targets meets our expectation, but we find that the appearance is still not satisfactory. So you can see that if we want to handle some high-speed dynamic videos, as shown show here, so you can see that it is very severe motion tearing. For example, for time 0, you can see that we have some motion misalignments. Time step 50 and 100, it has some still shifting, and on the other time step, you can see that it has a lot of high-speed blurring. So current video model, despite they meet the efficiency target, sometimes their quality is not that satisfactory on high-speed motion. And we quickly realized that actually we could try to improve it by control the noise level. So what I mean, so here that we can quickly estimate motions because we are talking about a video-to-video translation of live stream application. So we could analyze the motion in these input videos, and we can accordingly adjust the noise level based on the motion. For example, we could utilize inject more noise when the input video has very slow motion, and we could inject very little noise when the motion when the speed of the motion is high speed. So here we utilize the motion aware noise scheduler to improve the motion smooth. So as shown in these videos, that compared to our baseline without this motion aware noise scheduler, our stream diffusion V2 pipeline can have much smooth outputs. We almost do not have any motion tearing. And we also compare our method to our previous stream diffusion V1. So you can see that our method does not have any flashing, no, and it can keep very good temporal consistency at the middle video. And our pipeline is also a product level ready to this is ready to use. For example, this is one demo from the first author of the stream diffusion V2. So you can see something interesting here. So basically that we are doing the live stream. Actually, this is a real application. We also consider the camera latency, camera and the remote. So basically this model is work on the remote workstation. So there's some networking latency. So you can see this is why there are some delays. And you can also see that when we input the text and click send, we can the video model can quickly react. Yeah. So the video just now is a 1.3 billion model, and we can also achieve real time very high FPS on 14 billion. So you can see the quality is much higher compared to 1.3 billion model. Okay. Yeah. So this is our work about stream diffusion V1 and stream diffusion V2. So we're starting from stream diffusion V1 that we use image-based model, and to improve the temporal consistency, we utilize the video diffusion model, and we can achieve very temporal consistent video-based live stream. And what's next? So basically, as I mentioned in our technique, we try to shrink the input size. So in that case, we could push the workload from a heavy compute bound to a memory bound, and then we could control the batch size and to like improve the IPS and so on. So a very natural like question can be thought. The hardware is keep improving. Will the memory, so will we still make the easily make the whole pipeline always position on the memory bound region? Actually, I want to give some like outlooks here. So you can see that even though the GPUs like is keeping improving, for example, from V100 to A100 to H100 to current like B200, you can see that computation capacity increased by 16 times, by 17 times, but the memory bandwidth of these GPUs only improves by 7 times. So you can see that the memory bandwidth of the GPUs improves much less than the computation capacity. So this means the GPU, like the memory will always be the bound of the current workload. On the other hand, we also find that the algorithm development also push the video generation model into a more memory bound region. For example, current VAE is a really good like compression technique. For example, 1.2 VAE is very strong, and basically it can compress the raw video into kind of small size. But if you look at 2.2 VAE, this kind of algorithms is keeping improving, and they try to compress the video even smaller. So for example, if I remember correctly, the 2.2 VAE compressed video 4 times more than 2.1 VAE. So this means that the input size of the video will be even smaller. So as I mentioned before, we want to make them smaller and try to push the whole like workload into memory bound. So this means that not only the hardware development try to push workload into memory bound, the algorithm development also push video generating models into a more memory bound region. And then this comes to a very familiar problem for LLM, because in LLM community, all the current autoregressive models are most of them are heavy memory bound, and memory always being a bottleneck in the larger model. But now memory are gradually becoming a bottleneck for video generation model. So here's two demos from most like popular video generation model like long-cat video and Hongyan video. So you can see that in long-cat video, 720p and 8 frames, only like the KV cache, just KV cache, like could occupy almost 68 gigabytes with like BF16. And for the Hongyan video, that just KV cache like occupy like 21 gigabytes. So this means that like for the left video, so just KV cache occupies so much memory. This means that we can only utilize the GPU like H100 GPUs to run this video generation model. And even worse, the memory bottleneck makes the video generation model hardly handles the long horizon drift. So this is a demo. You can see here. You can see the video gradually like drifts. So this is because we can only keep very limited KV cache, and we cannot like really capture what they generated before. So the error would accumulate like after the long horizon video generate. So you can see this the video begin to progress. So we want to improve this. So we want to make the video generate model work on not only work on like H100 or B200 GPUs, and we can also improve the long horizon drift issues, like try to compress the memory. And we quickly realized that in video generation model, there are so many redundancies. For example, we have spatial and temporal redundancy. As shown in the left figure, we try to measure the temporal frame distance. You can see that most of the tokens has very high similarity. For example, like they in average they'll achieve like 0.8 cosine similarity from the temporal nearby tokens. And for spatial cosine similarity, you can see that they are also like the nearby spatial tokens are also very similar in the right feed. And this inspires us to propose a semantic aware grouping method. So what I mean, so we want to like compress the KV cache, and now given let's say the key cache here, this is a key cache tokens distribution. You can see its original very irregular and very hard to compress. Here we want to quantize them, and because actually the tokens could be very similar in semantic way, and we can try to utilize basically we can try to utilize a very like a semantic aware based method to group the similar tokens together. Basically, we can like try to reorganize this key key cache to make similar tokens like put together as shown in this figure B. And in figure C, that after we put them together, we can subtract the centroid, and then we can transform the irregular part to quantize cache distribution into a regular and sparse distribution, which is very easy for us to quantize it. As shown in the figure that we can make distribution, the original distribution very they are very kind of separated. And now after we put them together and subtract the centroid, then we can make them merge together. So this is quite easier for us to do the quantization. And this is our pipeline method here. You can see that given the original cache, we can try to group the similar tokens together by it as a k-means. And with the k-means, we can then subtract the centroid, and we can get the residuals. And we utilize this method progressively to make the numerical become sparse and easy to quantize. And you quickly realize that, okay, we progressively utilize k-means to reshape the distribution. But k-means is always slow in our mind, right? Actually, actually in our previous work, it's as we call the sparse video gem. At that work, we already resolved this problem, k-means efficient problem, by proposing a flash k-means. So I'm very proud to share this with you, that we make k-means pretty fast. As fast to know that we are almost 10 times faster than current SOTA k-means method. So you can easily utilize our flash k-means by just pipe install flash k-means. So with our flash k-means, we can make k-means really fast, and whole quantization, the whole quantization pipeline only just only cost 4% for additional overhead. So this is very minimal, and so I'm very happy to share this with you. And with our technique, we are almost the first one to enable efficient long-tail video gen on our RTX 4090. For example, the upper video is the Kimi. Oh, sorry, the left video is the Kiwi, and the right figure is ours. So you can see that we almost do not have much long horizon drift here, but the TV method quickly drifts. And more importantly, our method is, as you can see, that we not only make the vision model run on very efficient memory, we can also significantly reduce the long horizon drift. So the left is the bema I showed before, and the right you can see that after you make the cache smaller, we can significantly improve the long horizon drift by increasing the number of tokens in the KV cache. So memory is bottleneck. Memory makes the video model hardly work on chip GPU or local GPUs, and memory issue also make the long horizon drift issue significantly in current this video gen model. So we want to improve the memory and make them more make them better. So this is the track of my video image diffusion. So I start from stream diffusion V1 and to V2, make them FPS higher, make them throughputs higher. And in our recent work, quantum video gen, we try to make we use less memory. In that case, we could make it on cheaper GPU and further improve the long horizon drift issue. So all of them I show is entertainment, right? So we can utilize video models to design some entertainment applications. But beyond that entertainment, what else? So we believe that the video gen models could significantly push the development in graphics research. For example, this is a potential new paradigm for graphics. This is also a demo from another user in our stream diffusion. So basically, that previously, if you want to render high quality fluid such as water and fire, it's very slow, it's very expensive. But now with our efficient image model, vision model, we can utilize low quality renderer plus our efficient video model or image vision model to render high quality fluid such and water and fire and strong here. On the other hand, myself also has a great interest in robotics, as shown here that it is a potentially new data pipeline for robotics. For example, given a robot data image or videos, that we can utilize this efficient video generation model or image model to translate one kind of robot to another kind of robot. So this can significantly reduce the efforts of the robot data collection. This is very important because scaling the robot data can potentially solve the robotics problems. There are many debates. Basically, there are many debates. Some people think no, scaling will not help. Some people say, oh yeah, it may help. But anyhow, I don't want to make this debate today. I just want to provide a new kind of scaling method for the robotics community by utilizing video diffusion models. So basically, that the robots have very different embodiments. So if we can utilize our method to always augment one kind of robot to another kind of robots, then we can increase the number of the robot data significantly. And we propose the OGE technique. So this is a scalable embodiment augmentation tool based on simulation technique and generative models technique. So basically, given one kind of robot video, we can translate one kind of robot into other different robot data. And we have a whole bunch of OXC data set collected from different lab, and we can utilize our technique to transform all of this robot data into other kind of robot data. So we can significantly augment the robot data, the number of the robot data. So basically, that's there are 16 types subset in the OXC data set, and we augment them by 9 times. So this can significantly improve the number of the robotics data. Okay, yeah. And is this robot data useful? Yes. So basically, that's, as you can see, after augment this robot data, we can make some transfer robot policies work pretty well. And you can check our website, and the data set is also released. The tool is also released. Yeah. So I'm trying to finalizing my talk by posing some visions here. So I talk about image and video generation models, and we utilize these generation models to augment the robotics. So it looks like very two different domains. So one is for Chenfeng AI, one is for robotics. So what's the connection here? Data is running. So Ilya, he said that data running out is a fundamental constraint on the scaling loss we have but one internet. But I'm kind of disagree with that, because he only considered the internet data. But actually, when I'm talking, when we do our daily life, we are generating data. So basically, that what I'm talking now, it could be posted, and basically when I behavior in front of the desktop, we are also basically we are also creating something. So we are doing some actions. But how could we collect this daily life data? Actually, the intelligent machines are key to create a data flywheel. So what that means? It means that actually we could build a closed-loop ecosystems between the intelligent machines and the machine learning models. For example, after we make the machine learning models more efficient, and then we can deploy it on our intelligent machines, like our phone, the robots, our AI headset. So this could utilize. So this basically generates some new data based on our daily activities, and this new data could further be utilized to train these machine models to make them more powerful. So basically, the powerful machine learning models enables powerful intelligent machines. If powerful intelligent machines make more people would like to utilize them, and they can create more data to further train these machine models. So we want to build these closed-loop ecosystems between the intelligent machines and machine learning. And I believe that robots and intelligent machines are the interface to the real world, and it can further drive the AI technique improvements. So yeah, I believe that this needs the two different community to push them together. And finally, that's so this last page of my slides, and I'm happy to share my research, and I'm very delighted to collaborate. Currently, I'm working on Together AI, and soon later, I would start my new lab at UTelsting, and very happy to welcome you to join and collaborate with my lab. And I also welcome you to join our Together AI to work with me. And thank you so much. This is all of my talk.
Thanks a lot. Thanks a lot for the very nice talk, and I'm super interested about meeting again to discuss more about efficient video models and so on. I guess we have some question in the chat, so maybe I can ask first question from Thomas Wies. So I think it's a question about like video diffusion. So does video diffusion also have the equivalent to pre-fill and decode phases of LLMs?
Yeah, this is a very good question. So far we don't have this because we are doing more like video to video translation and text to video generation. So I would more treat them like very similar to previous pre-filling stage, and but in the future, so people really care about word model application. For example, word model application means that given one input video, and we want to utilize this like these input videos to generate the other video or future videos. I would treat this more similar to LLM, like given the input video as previewing and decode the future videos like decoding. So I think this could be very equivalent. Yeah.
Okay, it's close. Yeah. And Thomas like says makes sense. So thanks a lot. Yeah, a question on my side is like I guess in a lot of the works you presented, like streaming diffusion and streaming diffusion v2, there is a lot of like autoregressive parts, let's say, in the model. But there are also video models that are not autoregressive, kind of. And so I was wondering, like, what is your take about like the power of non-autoregressive models against autoregressive models for video generation?
Yeah, this is a very good question. So there are two kind of popular video generation models. One is like bidirectional models. They are not autoregressive. And like recently, like self-forcing, cause VID, and also stream diffusion v2 based on them. So they are autoregressive model. So like in our like first intuition, the bidirectional model always have better quality, but they are limited by they're quite limited by the computation cost, so they can only generate very future short horizon video. But autoregressive model can generate 1 minute, 5 minutes videos, but the quality is lower. And so basically, that currently they have advantage and disadvantage. But I believe, like in the future, they will merge together. So it's more like, for example, I believe they're more like bidirection plus like calls. Or for example, actually current pipeline already similar to that. In a limited chunk, we are doing the bidirection, but like outside the chunk, we are doing the causal. So I believe in the future, people will better trade off the bidirection and the causal to trade off the like long horizon generation and visual quality. I would not only stand on one side, but I believe we should push them together to merge them together, but consider system level optimization, consider everything level optimization. And I also think that it's all really depends on our application. For example, if you want to do a live stream, like stream diffusion v2, we really care about efficiency. Maybe we should like lower the quality, so we will bias to more like autoregressive. But for some, let's say recently the CDS 2.0 is really amazing. We don't care much about the efficiency. We can wait for 1 hour to generate really high quality videos. So that means maybe we can bias more to like quality. So I think it depends on, we should push them together to merge them together, but at the same time, it really depends on applications. Yeah,
that makes sense. Do you have already some recipes on how to push them together? So I guess, for example, in streaming diffusion v2, you worked with 2.1, I think, which is by default non-autoregressive, but then you transform it kind of in like an autoregressive model. So maybe you can explain a bit how it works.
Yeah. So basically that's we first so we utilize 2.1 VAE, but our DIT is still we utilize the cos VID, this kind of like auto-regressive model. So and cos VID is distilled from 2.1 models. So I believe that a transfer between a transfer from like to bidirectional model to autoregressive model we create distillation. But honestly, I think we can do better. For example, maybe in the future we don't have to always distill from bidirectional model to get the autoregressive model. Instead, we can directly train train it from scratch, like train a like autoregressive video model from scratch. And yes, I think that's something we could do in the future.
Okay, super cool. Maybe I have a last question on my side. Like, maybe there will be some more questions also in the chat. So maybe a last question for on my side is like, here you show the applications of like streaming diffusion for streaming, use cases. But it looks like you can use it also for like faster video editing, kind of. So you could also give directly a full video and edit the video like faster and having a faster responsiveness of the modem. I was wondering if you look at this direction and how maybe if you feel that it will not work, or are you?
Yeah, one of my SML submission is about it. We can do linear video editing. Yeah, it's very interesting. Yeah, we can do that. We already do that, and we are it's a teaser. We will release them soon. Yeah.
So this is well that you're working on this. Yeah. So I mean, then we have to waken you again. So,
Thank you so much.
there is another question in the chat. So how ready are it for scale for real world applications where quality is not most important?
So I would say our streaming diffusion, like V1 and V2 are already ready for like live stream. So for example, that if we could if the like live stream company could provide the cloud service, basically that we can already this cloud service could provide the GPUs, like for example H100 GPUs or A100 GPUs. It's almost it can achieve like target IPS and the test the time to the first one. But the problem, this is kind of out of my field. I'm not sure whether this could lead some problem on large scale. For example, we already show that we can serve for one user and 2 users. I already show actually I tried to in 2 users, it's okay. But I'm not sure whether for hundreds of users, like 10,000s of users, whether it can still work. I'm not sure that. So I think this is a networking problem. Like I would give this to system people, and potentially I can talk together AI leadership whether they have ideas. I'm not sure I can do that. So I think just take this as example. I believe that the large scale would be a problem. There are many networking problems there. Yeah. But for the other applications, I'm not that familiar with like world model things. So but I'm very confident about live stream thing. This is what I will. I only worry about large scale issue. Yeah.
Great. One other question I have is like, I didn't know about this paper, the last paper you presented about like the large data set for robotics. So where does it come from, this idea of making like large data sets usable for robotics? Did you have some discussions with people saying okay they are super interested, or it comes really from the newspaper article you shown on the slide?
Yeah. This is a very good question. So first, that when we like did the research stream diffusion V1, we started from like the end of 2023, and at that time, many people have great interest, including myself as well, have interest in robotics, and we call it embodied AI, and recently is really popular, and all of us really stuck by the data issue, and we realized and actually that I'm just walk around on Bear and in Berkeley, I saw there are many different robots and people are using teleoperation to collect robot data. So I'm just thinking about why not translate this one robot data to another robot data, and then this might helpful. And I talked with my collaborator Lawrence Chen from another lab in Bear, and we think this could be useful, and we just do it, and we did the first work called called like Roviog is get assigned by Coral, and we realized this Roviog is just small scale. Why not we do bigger? We make the current largest data set, Oxy data set, being augmented, and recently we make it bigger, but it has more advanced simulation technique and the generation AI technique. So this is the things.
Super cool. It's a nice story. Okay. Thanks a lot for the great presentation. Okay, I think there are no more questions, and we are pushing to the end, so I can just close slowly this session. So again, thanks a lot, Chenfeng, for joining. That was really nice to have you and have all your knowledge about like efficient, the video models, and you have also great papers on language models. So again, check the real scholar of Chenfeng because cool people there. So thanks a lot, everyone. Just for to make like a last the message that also we are at Puna doing a lot of things on efficiency and a lot of things also related to what based on the research you are doing. And so we have like open source package, and we have also like efficient models that we have. So please feel free to try them. Otherwise, like take care and thanks a lot for joining the webinar.
Okay, thank you. Bye.
Thank you. Bye.
Bye.